All right, let's get right into it. We're about to explore a paper that proposes something that sounds like it's been pulled straight out of science fiction. We're talking about a machine, a simple one, that can literally take the heat from the air around it and turn it directly into motion. I mean, just stop and really think about that for a second. What if you could power something just by using the warmth of the room you're in? Or the heat in the ocean? It sounds impossible, right? Like, it's got to be breaking some fundamental law of physics. But a group of researchers think they've actually found a way.
And this is the number that makes you sit up and pay attention. The authors of this paper are claiming that their method could convert thermal energy into mechanical energy with efficiencies over 80%. That is an absolutely unbelievable figure. So, how in the world could that even be possible?
Well, this incredible claim comes from a paper detailing a whole series of experiments, and they're based on a really well understood but very cleverly applied area of physics. They started out just trying to see if they could use a strange little property of atomic nuclei, their spin, to create movement. But what they ended up finding was something much, much bigger.
You see, the entire secret, the absolute key to this whole thing, is happening down at the atomic level. It turns out that the nucleus of certain atoms behaves in this really peculiar way, kind of like a tiny wobbling spinning top. And the thing is, if you can learn how to control that spin, you can control a whole lot more.
The science behind all of this is called nuclear magnetic resonance, or NMR. Now, you've probably heard of its most famous application, MRI machines in hospitals, right? The basic idea is that some atomic nuclei act like microscopic magnets, and if you put them inside a big magnetic field, you can start to, well, play with them using radio waves.
So here's step one. You take a material, you put it in a really strong magnetic field, and all those tiny magnetic compasses inside its atomic nuclei, they kind of snap into alignment with the field. It's like they all suddenly decide to point north at the same time. Pretty straightforward.
But here's the cool part. They don't just sit there perfectly still. They also wobble, or precess. This diagram shows it perfectly. Just imagine a spinning top when it starts to slow down. It doesn't just fall over, right? It kind of wobbles in this slow circle. Well, these atomic nuclei are doing the exact same thing.
Okay, so if these things are like little spinning tops, what happens if you give them a little nudge? You can actually do that with a super precise pulse of radio waves. And as you can see here, that pulse can literally knock them out of alignment, pushing them into a higher energy state.
And this is what led to the first big test. The researchers had this amazing hypothesis. If you can flip billions and billions of these little atomic spinning tops all at once inside a solid object, could you actually make the entire object move?
Now, the reason this works comes down to a fundamental law of physics: the conservation of angular momentum. It's the exact same reason a figure skater spins faster when she pulls her arms in. The universe just doesn't like to change the total amount of spin in a system. So, if you suddenly flip the spin of all the nuclei inside an object, the object itself has to rotate the other way to keep everything balanced.
And this is the beautifully simple experiment they built to test it. They took a disc made of bismuth, which is a material that's perfect for this kind of NMR stuff. They put it between two powerful magnets, and then they got their radio frequency emitter ready to go.
And guess what? It worked. When they zapped that disc with the radio pulse at exactly the right frequency, the disc physically moved. Now, it was a tiny little rotation for sure, but it was undeniable. It was proof of concept. They had used radio waves to make a solid object turn.
But believe it or not, that was just the warm-up act. I mean, proving you can create motion by pumping energy in is one thing. The next question was way more ambitious. Could you get those nuclei to draw the energy they need from a different source, like, say, the heat that's already in the material? And that led to an even crazier machine, one that actually gets cold as it runs.
So this is the next prototype. And you'll notice there's no radio frequency pulse needed for this one. Instead, it uses a set of rotating magnets that pass by a cylinder made of really thin titanium sheets. The whole idea is that the moving magnetic field itself is going to be enough to agitate those atomic spinning tops.
And the results from this experiment were just incredible. First, they noticed that nothing happened at all until the device warmed up to about 30 degrees Celsius. Then, suddenly, the titanium cylinder started to rotate on its own. But the truly mind-bending part, the part that changes everything, came from an infrared sensor they had pointed at it. As the cylinder was spinning, it started getting colder than the rest of the room.
This could only mean one thing. This device wasn't just spinning, It was actively pulling thermal energy, heat, out of the metal itself and converting it directly into the mechanical work of rotation. It was a true heat engine, getting cold as it ran.
So, how on earth is this working without an energy pulse from a radio? Let's walk through it. As those outer magnets sweep past the titanium sheets, the magnetic field is constantly changing. This forces all those tiny atomic moments inside the titanium to scramble, to constantly try and realign themselves with this shifting field.
But where does the energy for all this realigning come from? Remember, there's no radio pulse feeding it energy this time. So, to make that jump to a higher energy state and reorient, the nuclei have to grab energy from wherever they can. And the only source available is the vibrational energy of the atoms in the metal around them, which, is just a fancy way of saying heat.
And this happens over and over and over again, billions of times a second. Every single one of those tiny reorientations adds up to a net change in the total angular momentum. And just like in that first experiment, to keep everything in balance, the entire cylinder has to spin. It's this incredible cascade of tiny atomic events that produces a visible mechanical motion, all powered by sucking the heat right out of the metal.
Okay, so this is amazing. We've got a little lab prototype that turns heat directly into motion. But what's the real-world payoff here? Why does this matter? Well, this is where the research takes a truly exciting turn, because it turns out the perfect fuel for a machine like this is, well, it's everywhere.
Seawater. It is absolutely jam-packed with elements whose nuclei have the exact magnetic properties you need for this to work. We're talking sodium, chlorine, potassium, even the hydrogen from the water itself. They're all potential fuel sources, just floating there in the ocean.
And the amount of energy we're talking about is just staggering. The paper points out that for every single cubic meter of seawater, there's about 1 kilowatt-hour of thermal energy available for every single degree Celsius you can cool it down. That is a ton of energy.
And look, this isn't just some far-off theory. The paper actually concludes by saying they successfully did this. They took a saltwater solution in the lab and proved they could convert its own internal heat directly into work, cooling the water down in the process. I mean, think about what this could mean for something like desalination, which takes a massive amount of energy. You could literally use the energy in the saltwater to help power the plant.
So that brings us to the final, really big question. Obviously, this is very early-stage research, but it opens up this incredible, tantalizing possibility. We're always looking everywhere for new, clean energy sources. What if one of the biggest and most powerful has been hiding in plain sight this whole time, in the simple warmth of the oceans themselves? It's a pretty powerful idea to think about.